Alright, this lesson is about rational functions. It's the first of two lessons. In this lesson I'll define them and describe asymptote behavior and something called holes. So first of all, a rational function takes the form f of x, it's a function, that is the quotient of g of x divided h of x. So g and h are two other functions that are polynomials, and h isn't 0. So basically what we're saying is divide a polynomial by another polynomial, you get a rational function. This is very similar to how a rational number is the quotient of two integers. If you think of polynomials being like integers, then their quotient forms a rational function, or, pardon me, I think I said that wrong. If you form two integers quotient, their result is a rational number. If you take the quotient of two polynomials, you get a rational function. Some examples of polynomials. If I had y equals x plus 1 over x minus 1, that's a linear function divided by a linear function. Or y equals x squared 5x and 6 over x and 2. This is a polynomial function. Now, notice that this polynomial function could be factored on the numerator to x plus 2, x plus 3, in which case I can actually reduce it to x plus 3, which is just a polynomial. In the same way that the number 3 as an integer can be written 3 over 1 and made into a rational number, polynomials are actually rational functions. If I think of h of x being a constant, then a polynomial divided by a constant is rational because a constant is a polynomial. Now there are lots of examples of things that aren't rational functions. All I need to do is write something that's not a polynomial function. So if I said something like y equals square root of x plus 1 over x minus 1, the numerator is not polynomial, so this quotient doesn't form a rational function. Anyway, moving on. Asymptote behavior is quite important, and we need to spend some time on that. Asymptotes are boundaries, or a boundary line, that graphically a function will approach but never touch. It just gets nearer and nearer. There are three types. Two of them come up quite commonly. The third one I'll mention. The first of them is a vertical asymptote. A vertical asymptote or boundary line would have equation x equals number. I'll write that down. Vertical lines take form x equals some number. For example, x equals 1 or something like that. It occurs at a domain value of a simplified rational function that causes division by 0. So we get division by 0 if a denominator is 0. A couple of examples. Here's a rational function. I can't simplify this rational function. There's no common factors to remove. So division by 0 is caused when x minus 1 equals 0 or when x equals 1. That is a vertical asymptote. The next function I've got here is factorable to x plus 2, x plus 5, and the denominator factors to x plus 2, x minus 2. So this can be rewritten as x plus 5, x minus 2, and there would be a vertical asymptote at x equals 2 only. Now, x equals negative 2 is something called a hole that I'll talk about later in this lesson. If you looked at it graphically, you would see why, and perhaps we should take a moment to do that right now. So I'm going to take, I have a few different functions entered here, and I'm just going to enable the function I want to talk about right now, which is the first example, negative 2x plus 3 over x minus 1. So if I graph this, I will see a behavior vertically. When x equals 1, I'm getting this kind of boundary condition I'm talking about. The graph gets closer, and here as well, but doesn't touch. Also, turns out there's a horizontal asymptote. I'll talk about that in a minute. If I go to zoom 6 to see a different window rather, I'll see the effect even more pronounced. At x equals 1, we can see how the graph is tending toward it, but yet not touching it. Now I can look at this with a table of values as well and show you what I mean. If I type in values near to 1, like 0.5, 0.9, 0.99, what you'll see is that the values are getting larger and larger and larger. So I have a negative 1,000 when I'm very near to 1 and yet less than 1. If I'm slightly more than 1, like 1.001 to the right of 1, I get very large positive values. Again, looking at the graph over here, you'll see for values less than 1, I'm going to very large negative results. For values that are more than 1, I'm going to very large positive results. Now, horizontal asymptote behavior. This is a little bit trickier. It's associated with end behavior, which you may recall is when x approaches plus or minus infinity. There's two procedures for finding this. The simpler of the two is to recall that as x approaches infinity, a polynomial behaves like its largest degree term. So what we can do is pay attention to the largest degree term of the numerator and denominator only. Here's an example. Again, you'll notice it's the same one from before. So as x approaches infinity, this function behaves like negative 2x over x, which is negative 2. So y equals negative 2 is the horizontal asymptote. It's as easy as that. Let me show you the graphical image again. You'll recall y1, there's the function we're talking about. Here's the graph of it. And look, as y is negative 2, I get this horizontal behavior where it's getting very close to negative 2. If you are doubting that, let me actually plot negative 2 for comparison. Y equals negative 2 is a horizontal line. Looking at it graphically, you can see that it's trending to that line. Now, it looks like it touches it, but that's actually an anomaly of how the calculator shows graphs. Again, if I tried values in a table of values, and delete the values that we did for vertical asymptotes, remember horizontal asymptote behavior is about large x. So what about x is 10? Well, the value of y1, the function I'm looking at, is negative 1.88. As I go to 20, 1.947, go to 50, you can see the trend that the result of the function is closer and closer to negative 2. It would be the same if I did negative values. If I put negative 100 in, I will also see a result very close to 2. This one's slightly more than 2. And that has to do with the fact that this is behavior to the left, whereas the previous ones were behavior to the right. Okay, back to some other examples. In this function, as x approaches infinity, I can say that the numerator behaves like negative 4x, the denominator behaves like 3x squared, which is negative 4 over 3x. Now, consider a very large x value. The denominator is huge. 4 divided by something huge is essentially 0. So this has a y equals 0 horizontal asymptote. Third case, as x approaches infinity, f of x is essentially x squared over x, which is x, and there will be no horizontal asymptote in this case because x is growing very large. This is not bounded. This doesn't head toward a specific number. So not all functions have horizontal asymptotes. Likewise, I should go back and mention with vertical asymptotes, not every rational function is going to have a vertical asymptote. You need the denominator to be able to be 0, and it won't always be the case. So we don't always get this asymptote behavior. Now there's a second procedure, it's a little more complex for finding horizontal asymptotes. This is often used in calculus. And what we do is we divide every term by the largest degree term. So looking at this rational expression, I've got x squared terms. So if I divide everything by x squared, I would get 3, and I would get 1 over x, and I would get negative 5 over x squared. The denominator would be 4 over x squared minus 1. Next, I consider very large x values approaching infinity. And I made an observation here that 1 over an x value for large x is essentially 0. So this function will become y equals 3 plus 0 minus 0 over 0 minus 1, or y equals negative 3 as a horizontal asymptote. All right. I wanted to talk briefly about a third type of asymptote, which is a slant or oblique asymptote. This one happens when your numerator degree is 1 more than your denominator degree. what you do in this case is actually perform the division, synthetic or long division, since rational functions really is a division statement, then evaluate the result for large x's. Again, here's an example. This one, because I have a linear binomial, will allow me to do synthetic division. So let me put all the coefficients in place, perform the operation of division, and get my remainder. So what I have found is that y equals x plus 2 plus a remainder of 1 over x plus 1. Now, as x approaches infinity, 1 over x and 1 approaches 0. So my slant asymptote will be y equals x plus 2, a line. You can graph this function on your graphing calculator and graph this line for comparison's sake, and you'll see that for very large values of x, they don't even have to be very large, that this rational function will behave like this line. However, it won't near the origin where x is negative 1. There'll actually be a vertical asymptote. Okay, the last thing I wanted to talk about is a hole. A hole is a strange little anomaly. It happens when you get an undefined value in a rational function caused by common factors shared by numerator and denominator. These are not asymptotes. They're not boundary lines. Here's an example. The numerator factors to x plus 2, x minus 2. The denominator factors to x plus 2, x plus 3. Canceling common factors by division leads to x minus 2 over x plus 3. This has a vertical asymptote. Maybe you should identify all the asymptotes. Pause for a moment. Okay, it has a vertical asymptote of x equals negative 3. It has a horizontal asymptote at y equals 1, the coefficients of the largest degree term, and no slant asymptote because the degrees are equal. And the negative 2 is an undefined value in the original function. It causes 0 divided by 0. It is the whole. Let's look at this one graphically, and I'll show you what I mean by this. So I'm going to turn off the first function, and I'm going to turn, actually I'll just overtype this with x squared minus 4 divided by x squared plus 5x plus 6, and choose zoom 4, which doesn't show it very well, so let's try zoom 6. And what you'll see at zoom 6 is there's actually a hole there if you trace it out.